we're here. We're talking about similarity, and proportionality is a thing that happens in similarity. It turns out, right, similar polygons is what we're talking about today. We'll talk about similarity, how that affects, Isaiah, the side lengths as well as the perimeter of a polygon. And then also we'll take a look at how it affects the areas of said polygons. And I think in previous videos I spoiled this lesson, so you might just remember some of this stuff. So it says corresponding parts of similar polygons in the diagram. This triangle is similar to that triangle. Makes sense? So Alyssa, notice this little symbol right here, this little guy, he's like not an equal sign, he's not a congruent sign, he's like, I don't know, he's just that. That means similarity. So equal, congruent, similar, and congruent has both equality and similarity at play.
Oh, just like that.
Yeah, so it's almost as if the equal sign and the similar symbol were the parents to the congruent sign. I'm guessing is what happened. So, this triangle is similar to that one. Notice that corresponding angles are all congruent. So you could scale this up or down using dilations, perhaps. And the angles maintain congruence. Well, the ratio of the sides, Jack, the ratios are consistent. Now notice what this is saying. They said that DE, the ratio of DE to AB, this ratio, if this is say like 3 times, Alyssa, are you with us?
No.
All right, don't worry.
Don't worry.
Let's say if this is 3 times the size or 4 times the size, that if this is 3 times the size, then this segment is also going to be 3 times the size of that one, and this segment is going to be 3 times the size of that one. That the ratio is consistent. The ratio of this one to that one will be a set scale factor. All right, so this is the idea of what we're doing. Let's do some examples together. Here we go. We're gonna do proportions. It's gonna be great.
Yeah.
Super easy today. All right. So here we are in the diagram. Triangle Erst is oh man, I almost said congruent. Are you guys with me, Terry? You with me? Isaiah, you have a seat, please. Yeah. Similar to triangle XYZ. Find the scale factor from Erst to X's. So I would compare corresponding sides. So the scale factor K is simply going to be, I don't know, like 25 to 15. Right? Actually, no, I did it wrong. Okay, they wanted the inverse, the reciprocal of that. So they would have done 15 to 25. My bad, friends. Which, what does that reduce to? 5 goes into both of those how many times each?
3/5.
Yeah, 3/5. And notice that scale factor is the same if I compared 18 to 30. Right, 6 goes into 18 thrice and into 30 fifths times. And it's also the same if I did the scale factor of this guy to that guy. So 12/20ths. So, yeah, what goes 4 goes into 12 3 times and into 20 5 times. Now, so I guess the way you could think about this is to go from this to that, you would multiply by 3/5, all of its side lengths. Okay? For B, it says list all pairs of congruent angles. So R is congruent. Well, they're not all congruent to each other. R is congruent to who? X. Angle T, man, I can't write this fast enough. Congruent to Z, and angle S is congruent to who now? Y.
R.
And then it says, write the ratios of the corresponding side lengths in a statement of proportionality. So, what I would say is that comparing those things, that XY is to RS as Now, so this is a ratio, right? Ratio. And a proportion is when I set two ratios equal to each other. So xy is to rs as xz is to who?
RT.
RT, yeah. And xz is to RT as yz is to
ST.
ST. You guys got it. You guys got it, right? This isn't that bad. Let's see. My laptop is too far away from me. All right. Let's do. Let's write this down. Or I guess you guys don't have to write anything down. It's already written. Okay. Corresponding lengths in similar polygons. It says if two polygons are similar, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor of the similar polygons. Polygons. So let's do example 2. Example 2, just for you. There we go. Good old example 2. All right, we're going to cruise through this, guys. We're going to do this in time. It says in the diagram, these things are similar to each other. Now, there's actually a whole lot of ways you could set this up. All right? I could say that x is to 30. All right? I want to compare the thing I don't know to one of the things I know. So x is to 30 as what? What's another fraction I could relate that to?
15 is to 18.
15 is to 18. All right, that's a perfectly legitimate setup.
Wait.
I also could have said, what if I said long side to short side? What if I said x is to 15 as what? As 30 is to 18. Okay, so I want to point out, like, there's actually so many ways. I want to say 6, but I feel like it might be 12, because you could also reciprocate all of them. Lots of ways that I could write proportions that are true about this. Now, in order to solve a proportion, once you have one written, you only need one. To solve it, you could, in this case, multiply both sides by 30, right? Because x is being divided, so multiply both sides by 30. That's perfectly good. But sometimes it can be easier, sometimes, not all the time, to cross-multiply. Do you guys remember cross-multiplication? Let's just cross-multiply just to get in the habit. So that would be 18 times x is equal to 30 times 15. So that's what, 450? Yeah. And then I could solve that. Okay? Not necessarily always the easiest way. In this case, it might have actually been one step longer. And I'm going to get, what, x equals 25? I cheated, actually. I've got the answer on my screen right here.
Wow.
Wow, Mr. Waddy is amazing at math. And no, I couldn't lie to you guys. I'm like mediocre. Maybe not even. But I was going to reach for a calculator for that. I think you feasibly could have done so yourselves. And you would have gotten no judgment, friends. No judgment from me. Question? No, you're just like poking a pin in the board. You're doing some Pinterest. All right. Here we go. Finding a corresponding length. All right, check this out. All right, in the diagram, triangle TPR is similar to triangle XPZ. So TPR, T to P to R, and XPZ. Okay, so these are like reflected then dilated versions of one another. Okay, so I'm just thinking of that. It says find the length of the altitude PS. What's an altitude again?
It's the height.
It's the height of a triangle. Okay, so I want to find this. I'll give that some name. All right. I guess, I don't know, X is fine, but there's a capital X here. Be careful. So I'm going to say X is to what? What's a proportion? Yeah, you could say altitude to altitude would equal what? I could say 6 to 8, right? Comparing this to this. I could have said 12 to 16, yep. right? I could have done that. Either of those would have been fine. Another proportion I could have done. I could have compared x to its own triangle. I could have said altitude to little leg guy in the right triangle is similar to what? 20 to 8. Okay, so hopefully you guys are comfortable with just the lots of different ways you could set those up. But let's solve this. Let's solve this. You're guessing? I don't know. So to solve, last time I cross multiplied, let's say this time I just, x is being divided by 20, so the inverse operation is multiplication.
More like 11 or 12.
Right? So that does in fact isolate the x. And watch this, watch this. This is what I do. Instead of doing 20 times 6 and then dividing by 8, do the division first. Because division makes numbers smaller, multiplication makes numbers bigger. True story. Like if you want to walk away with a fortune cookie today, that's a quote right there. I don't know. So let's see, 20 and 8. Can I cancel those out partially? 4 goes into 25 times and into 8 twice. Oh, and then I can actually reduce this. I could have actually reduced the 6/8 first as well if I wanted. 2 goes into 2 once and into 6 how many times? 2 goes into 6? Thrice. And let's multiply what's left over. 3 times 5 is 15. Okay? You could have solved the proportion a bunch of different ways. You could have set up the proportion a bunch of different ways. But there we go. And it doesn't just apply for triangles. It applies for all polygons when you have a relationship of multiple polygons being similar to one another. Here's a theorem. Now side lengths of any polygon, how do I find perimeters using side lengths? I just add them all up. So if there's a ratio between each individual side length here, okay, if K is to L as P is to Q, right? Or sorry, if KL is to PQ as KN is to PS, etc., right? If there's a ratio between all of those side lengths that is consistent, then shouldn't a perimeter, which has a formula of just adding up all the side lengths, also have the same, right, scale factor? The same ratio would apply, and that turns out to be the case. So if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. All right, so let's talk about Olympic swimming pools, angry face Michael Phelps. Here we go. All right, so here we go. A town plans to build a new swimming pool. Man, why isn't our town doing that? Oh, actually, wait, our town is kind of doing that, isn't it? Like over by like the Living Memorial Park? Or they did? I don't know. I just heard they were digging it up at one point. Maybe this is old news. I don't read the news. I just read the headlines. I don't know. I heard they dug and then they hit a boulder and then they had to throw 10 grand at the boulder to bribe it to move. So it says an Olympic pool is rectangular with a length of 50 meters. I can imagine that, like there's a picture on the screen. And a width of 25 meters, but no one knows what a meter is in America, sadly. The new pool will be similar in shape to an Olympic pool, but will have a length of 40 meters. So imagine, in our town, we're going to build a smaller pool that is 40 meters. Find the perimeters of the Olympic pool and the new pool. So they didn't ask me what this length was, although we could find it. They asked me to figure out the perimeter of those two. All right? Let's find the perimeters of the Olympic pool. So let's find out, what is the OP, the original Olympic pool perimeter? All right, it's a rectangle, so I could just do 2 times 25 plus 2 times 50. And I get 50 plus a hundo, looks like 150. So this is the OP. All right? Now the town pool perimeter, I guess I'll call TP. Town perimeter. I don't know. I could find this length using a proportion and say x is to 25 as 40 is to 50, and then redo an entire perimeter formula. But instead, what if I do this? TP, this perimeter, is to 150 as 40 is to 50. You guys do that. All right, so you guys have swam multiple laps of a swimming pool while you were waiting for me. I had to take a phone call. So perimeter to perimeter is equal to side, and that makes sense. I like it. Okay. Let's reduce this. Let's reduce this. I can just go swipe, and that's 4/5. And then let's multiply both sides by 150. Or you could cross multiply. If you're a fan of cross multiplication, you cross multiply. And I'm going to get TP, the perimeter of the town pool, is equal to 150. Let's do some canceling here. Divided by 5 is 30, right? And 30 times 4 is 120. I think it makes sense. And perimeter is measured in meters, not meters squared. It's not an area. It's a length around the pool.
Yeah.
I think Michael Phelps should not only have to swim a lap, but then also run the perimeter of the pool afterwards, and it'd be like a biathlon. Except not. Oh yeah, no running. No running. All right. I did not recommend running around the pool.
Don't run and swim, kid.
Yeah. Now, what about area? Now, guys, think about this. So, perimeter is a linear dimension. Side lengths are linear dimensions. But area, if I compare the areas of similar polygons, they are not set to the same scale factor.
What?
All right, so if k is to n as p is to, right, or kn to ps is as to kl to pq, if these are similar, right, their side lengths behave one way, their perimeters behave one way with a scale factor of k, but the ratio of their areas, right, if I find all of the little insides here, the ratio of their areas is equal to the squares of the ratio of their corresponding sides. And we did that a while back when I was like, how many of these could fit inside of that if this length is half of that length? And the answer was, right, if this is a 1 to 2, then the areas are a 1 to 4, because 2 squared is 4.
Right, so
You don't think this works?
so the ratio of the individual sides is the same as the ratio of the perimeter?
Yes, because perimeter is a linear dimension, side length is a linear dimension. Now, area is a squared unit, right? Linear dimension squared, and so the ratio of the sides needs to be squared in order to do that. Let's see. Here we go. So, all right. It says these guys are similar. Find the area of depth, and they said that the area of this was 36 centimeters squared. Now, let's see. So this is 10. This is 5, right? Yeah.
Right.
Okay.
So it'd be 10, 5.
So 10. So 5 is to 10 as some unknown area is to 36. Except wait, it's not this ratio. It's the square of that ratio.
What?
Because area is squared, side length is not.
How do you do that?
All right. You could square the entire fraction, or if it's easier for you, you can just think about squaring the top and the bottom. You actually, in this case, I should reduce that fraction and then square it, because 10 squared. What is that? Like 100? Come on, I don't think so, Isaiah. You and your imaginary large numbers. 5 divided by 10 is a half. Let's square it. Square 1. I get 1. Square 2, I get 4. Multiply both sides by 37. 36.
Why do you do it this way? I don't like this.
You want to cross multiply? You can cross multiply.
Yeah, good.
All right, let's do it. All right, cross multiply. 4a. Oh man, wrong color.
Oh, that's something.
Equals 36, and then divide both sides by 4. Same answer. You can choose your own adventure.
This makes so much more. A.
Okay, you don't like dealing with, I understand. So A equals 9, and that would be centimeters squared. Now notice 9 centimeters squared, right, fits into 36 4 times. Watch this. Let's see if I can do this with my drawing program. Let's see, where's my... Now I have no idea whether these are actually drawn to scale. Can I lasso tool this? Where's my lasso tool? Let me see if I can draw around this. And copy that and paste it. Let's see if this works. 1, count them, 2, 3, and then upside down 1, 4. I fit 4 of them in there. Wow. Wow. All right, guys, I think I'm calling it a show.
I count 5.
Shh, quiet. There's 4 up there inside, and then there's the 1 over there. All right. Oh, yeah, but you're counting the big triangle, the overlapping triangle.
Now I count 6.
Okay.
All right. Have a good day, friends.